Welcome back to the Lowdown on Physics. This is Screencast number 5 in a series on electric power for VCE Unit 4 Physics. Today we'll be looking at electromagnetic induction. Having just looked at motors, we're now kind of sort of doing a 180 flip on the aspect that we're looking at, and we're now sort of looking at the generation of energy. So electromagnetic induction is effectively the process by which magnetic energy can be used to create or is converted into electrical energy. What I'd like you to do is just recall back to wires when they were in a magnetic field that they were carrying a current. Now, using the right-hand slap rule, they experienced a force. What we're going to do here is effectively reverse that scenario. We're going to apply a force to a wire that's in a field, a magnetic field, and produce a current. You'll notice here that we have this rod. It's at right angles to the magnetic field, so as we move it to the left with a velocity v, it's going to be cutting those field lines. Now what's going to happen is that the electrons in the conductor are going to be moving relative to this field, and so they will experience a force towards one end of the conductor. And so we can basically use the right-hand slap rule to analyze this. The result will be that as it moves, the charges are forced in opposite directions, and we end up with one end of the rod that is more negatively charged and the other rod being more positively charged. So let's just have a look at that again. So we move that through the magnetic field, we cut those lines, and the charges are forced to either end according to the right-hand slap rule. Eventually we're going to reach a point of equilibrium because we can't keep forcing more and more negative charges to each end. So it's effectively, once you balance the electric forces with the magnetic forces, we kind of hit this equilibrium stage. So what factors would affect the size of the current that we're going to induce? Obviously, as it was with motors, the size of your magnetic field plays a massive part, and the length of rod or wire that you've got within that magnetic field, and obviously how fast it's moving. So the resulting, induced EMF, and we're talking about a potential difference here, depends on the three things that we discussed: the size of the magnetic field, the velocity that you're moving, and the size of the wire that you've got in there. Negative, well, that's got to do with the induction process. We'll talk more about Faraday's law later in the next screencast. So the induced EMF only occurs when it's moving at right angles. Okay, really important that it's got to be cutting through those magnetic field lines. If it's not cutting the field lines, then you're not going to have that interaction and induce any EMF. So let's look at an example. We have 50 centimeter length moving through a magnetic field of 2 Teslas, and we've got a velocity of 5 meters per second. We want to know the size of the EMF. So we've got our equation, we've got 2 Teslas, we've got 5 meters per second, and we've got 0.5 meters. Just be careful of your units. Always watch the centimeters. Make sure you get those to meters before using it in the equation. And the effective EMF that we're inducing is 5 volts. Whilst moving a single wire through a magnetic field is, in terms of a scientific discovery, a wonderful thing, it's not very useful for us in terms of using electricity, transmitting that electricity. So we need a continuous loop. We need the electricity to be able to flow around. Now, if we put the entire loop inside the magnetic field, you'd end up with a left-hand side and a right-hand side, both trying to push electrons in opposite directions of that loop. And so effectively, you'd cancel each other out. So what we need is part of the loop to be outside the field or in a weaker field. This is in just sort of taking it to that next step to create a flowing current that we're inducing. And then what we need then is the amount of field inside that loop to be changing. Now I find a diagram will help explain what that means. Now if we have only a section of our loop within that magnetic field, when this moves, there, see how we've got a full magnetic field here. As that moves, we will get less and less magnetic field inside that coil. So we've got to change the amount of field. So by cutting lines, it's effectively making less field, or if it was going the other way and this stayed outside, we'd be creating more field. So you have to change the amount of field, and effectively that's just by cutting the magnetic field lines and taking some out. That changes the amount of field, therefore allows an induction of EMF to occur. Now one other alternative would be by changing B, or varying the magnetic field strength. Now we can do this, so effectively you're not cutting any field lines in this scenario, and there may or may not be any motion between the magnet and the loop. So basically you've got a couple of options. You could move this magnet up and down, okay, therefore changing the strength of the field that's within that coil. Alternatively, if you had an electromagnet, you could vary the strength of that magnetic field produced by the electromagnet, and therefore change the amount of field lines within the coil, and therefore vary the induced EMF. Okay, so that's looking at it just with a single coil. So let's have a look at factors that are going to affect the size of the EMF. How do we increase the size of the EMF? So let's just look at a simple example. We've got a magnet. We're going to bring that down into a solenoid. Basically, varying this strength of this field, the magnitude of our induced EMF depends on this part here. Use a stronger magnet, then you're going to induce a larger magnetic field. If we bring this in slowly as opposed to bringing it in quickly, then we're going to get smaller. So velocity also affects the size of the EMF we're going to produce. Number of turns. So if we put more turns in, we're going to get a greater EMF. Why? Because effectively each of these coils is inducing EMF. So we're kind of, instead of just doing it for one coil, we're doing it for multiple coils, and so we're increasing it by a factor each time for each turn. So EMF is dependent on these things. Alright, that's it now for induced EMF. So I'll see you in class. We'll do a prac which will investigate these very things.